Hey everyone, welcome back. So last time we figured out how we got Bernoulli's equation, but I said that wasn't the technical derivation. So this time we're going to make it technical. So let's get technical here. And why we're doing this? For completion, and also so you know the math behind it. It's not super terribly important. You can skip this one if you want to, but I'm going to keep it here so I have it. Okay, so what we're going to do is we're going to start off with our conservation of momentum equation. So that looks something like this. We're taking all of our simplifications, so incompressible, inviscid, steady, no body forces, and it comes out to be something like the following. So u, del x, I'm going to do my best to call those dels because that's what they are, plus v, del u, del y, plus w, del u, del z, is equal to the negative of my pressure gradient. Okay, so we have that. Now, the first thing we're going to do is we're going to multiply everything by dx. Yeah, we'll multiply it all by dx. Okay. The reason for this is going to become very apparent in just a minute. But first of all, we'll go ahead and write it out. So what I get then is I have u, del x, dx plus v del u del y dy plus dx, still x's, plus w del u del z dx. I do my best here to say dels where they're supposed to be dels and d's where they're supposed to be d's. It's going to be equal to negative 1 over rho del p del x dx. Okay. Now, why did I bring the density over? Mostly so I would have an easier time writing out that. I wouldn't have to have a parentheses the entire time. And also so I would just go ahead and distribute that dx. Now, I've done that, and the next thing we're going to use is we're going to remember that this is along a streamline. So it's along a streamline. So it's along a streamline, I have certain equations that I can use. What are those? Well, I gave you equations for how you follow a streamline. And they look something like this. So you had, let's see, you had u dz minus w dx is equal to 0. You also had v dx minus u dy is equal to 0. Now, notice I have up here, I'm just going to kind of connect these here. This is right there. And this is right there. So you see, not that one. That one is right there. There we go. Perfect. So you see that both of those exist. And so what I can do is I can use these equations for a streamline to help me fix those and change those. So I'm going to go ahead and say that w dx is equal to u dz. And I'm going to say that v dx is equal to u dy. I'm going to take these variable equations, I'm going to plug it into my first equation, which I'll go ahead and call this 1 just to make it easier and call these 2. So I can go ahead and say that I'm plugging 1 into 2, or sorry, 2 into 1. There you go. Now, when I do that, what do I get? Well, I get an equation that looks much more ordered in my opinion. So u del x dx, that's the same. I'm not doing anything with that one. Plus, and this is where things change, I now have u del y dy. Do you see where I'm going here? The u's match up, the x's match up, the u's match up, the y's match up. And finally, plus u del z dz. There we go. It's going to be equal to negative 1 over rho del p del x dx. Okay, so I have this. And the glorious thing is, calculus helps us out here. Now, never tell a mathematician this, but engineers, we actually do use calculus. We do use math. We just don't do all the work. We let the mathematicians do the work for us, and then we come and we steal it and use it for our projects. So don't let them know this. They might start getting on to us about it. But for now, it's really helpful. And if you ever meet a calculus person or a math person, give them a hug. Don't tell them why. Just give them a hug. And if they look at you weird, just say, thank you. Thank you. Okay, so from calculus, if we have a function, so in this case, my velocity, and it's a function of x, y, and z coordinates, well, then I know that the derivative of that function is going to be equal to del u, del x, dx, plus del u, del y, dy, plus del u, del z, dz. And so I have this right here now. You might have seen these before. All of this stuff is up here. And so I can now simplify this dramatically. So my equation goes from a long, big equation that goes down to u du is equal to negative 1 over rho del p del x dx. And this is really, really close to how I got Bernoulli's earlier. But this is just for the x component. Earlier we were doing it for the total velocity, not just a component of the velocity. So let's do it for all the components, okay? Now I'm going to write this entire process out again. I'm just going to say we did it for all of them. And I'll go ahead and give them to you right here. So I have x component, I have the y component, and I have the z component. And just for later, I'm going to go ahead and say this is 1/2 d of u squared, because that's what it would be. And that's going to be equal to negative 1 over rho del p del x dx. I do that for all of them. So now it's 1/2 dv squared is equal to negative 1 over rho del p del y dy, and 1/2 dw squared is equal to negative 1 over rho del p del z dz. That looks good. I got them all. And so what I can do then is I can add all of these together. So I'm now going to add them together. And that gives me the following equation. 1/2 of d u squared plus v squared plus w squared is equal to negative 1 over rho. There you go. Times, I'm just going to run out of space right here, so I'll go ahead and put it underneath it. 1 over rho del p del x dx plus del p del y dy plus del p del z dz. Okay, and earlier we called this u, the whole velocity. We called it as this kind of uppercase u. And this right here we learned from physics is actually just equal to dp. So if I know that, this simplifies dramatically. And what do I get? Well, I get the 1/2 d, my total velocity squared, is equal to negative 1 over rho dp. And if I integrate both sides of this, I'm going to integrate, and what do I get? Surprise, surprise. I get that my pressure plus 1/2 times the density times my total velocity squared is equal to a constant. Okay, there it is. We did it. We got to the same exact answer, just through a more correct way. You saw some calculus. You learned that calculus people and mathematicians are super important. And we figured out how we got to Bernoulli's equation. So thank you all for listening, and I'll see you all next time. Bye-bye.